Okay, yeah, thank you everyone for being here today. My name is Tomás, and I will be presenting our work with Kenji, Nicolas, and Éric, where we study how to work incrementally with certified programming. And with certified programming, I mean writing programs and writing their specs, and then proving that these programs are correct, all within the same system. And where one important aspect is that the process of programming and proving is deeply synchronized. So for instance, if we introduce a bug in our code, we know that we can immediately catch it during the proving process. And we cannot prove it because the program doesn't satisfy the specification. Or in the same way, we could, for instance, for any modification that we make in our code, we necessarily need to go and update our proofs because, once again, the programs don't satisfy their specification. And so this synchronization between programming and proving is crucial for certified programming, and it's at least one of the things that differentiate from pen and paper proofs. And there are several systems where we can do this. We have Rock, Lean, Agda, and many others. And so what we were interested in was on how do we build these certified programs? How can we get to this fully defined program and this fully finished proof? Because one alternative could be to just follow a classic traditional kind of waterfall approach where we first define completely our definitions, our program, and only then we go ahead and prove it correct. But we were interested in seeing what happens if we wanted to follow a more agile or incremental approach where we could define our program step by step and leaving parts unimplemented. And so the first question, and of course with that we can do the same with our proofs. And so the first question is how do we define these incomplete programs? And I will be using this whole symbol to refer to unimplemented code. And there are several ways. For instance, we could have axioms. We could have a to-do axiom that inhabits any type, and we just plug it in the hole. We could have monads with specific constructor cases to refer to unimplemented code. We could have exceptions if we had full support, like in any mainstream programming language. And then there are many, many, many other options. And in our work in particular, we explain a little bit more about these different approaches, but we don't specifically focus on this aspect of incremental programming because it shares some concerns with non-certified settings. So instead, we focus more on the proving side of certified programming. And in particular, how do we manage proofs when in the presence of partial programs? Because as soon as we have incomplete programs, we immediately start having issues. And this is mainly because our specifications are designed for the complete versions of our programs, and of course, then they are not valid for intermediate states of development. And so this means that whenever we have a hole in our program, this will eventually show up in the proofs, and of course we will get stuck, and we won't be able to do anything. And so one alternative is to try to circumvent this. The easy way is, for instance, in Rock we could use the admit tactic and just skip the proof and do nothing. But this is effectively breaking this synchronization between programming and proving, because now any change in the code is not reflected with a change in the proof. And so the issue is that, for instance, we could introduce bugs and we don't see them reflected in their proofs, among other things. And so what do we do with this issue? And what is it that we really would like to have if we were working incrementally? And I'm going to do an idealized incremental scenario where we are going to assume that we fully support this practice and to see kind of the things that we would like to have. And so for the scenario, I'm going to assume that we have some interpretation function that takes some input from some type term, which is some big index type, and returns some terms of type val. And we'll assume this is complete for now. And what we actually want to do is define this optimization function, which will start just by putting a hole. We don't know what it's going to do. But the only thing that we do know is that it should preserve the semantics of the interpretation function. And so the first thing that we would like to have is, in the same way that we put a hole in the definition, we kind of would like to just say, oh, this is trivial, there's nothing to do. I haven't done anything with my definition, so QED. And then, of course, because we're in an incremental scenario, we're going to add a little bit of code to our definition. And we would expect that our system will flag this as, hey, the proof is no longer trivial, you have to do something. And sure enough, we did something, so we're going to go ahead and prove it. But the important part is that we only programmed what we needed, and we only proved what we added to the code, and nothing more. Then a second thing is that the proofs should be stable. And by this I mean that, for instance, if we add a second case to our implementation and we fix the proof, the existing proofs that were before, they should remain valid. We shouldn't need to touch them, and they should remain valid. And of course, again, we should only care about the new code that we added. And also, is that, for instance, what happens if we found that this is not provable, there's some error. The only two options that there should be is, first, that we either introduced a bug, or that the specification was not correct from the beginning. But at no point should we need to fill in the hole, right? The incomplete code should have no effects on the proof that we're doing. And then, so we can continue the process, we can implement each step of the way until we reach our final version of the program and we prove it correct, and we're happy. And that's the final part of the idealized scenario. And so the question is, how can we do this in a systematic way, and that we actually get our end result, what we wanted, and very importantly, that each step of the way the programming improving parts are synchronized. And one thing that we think is crucial is the fact that properties should be incremental. So in the same way that we can code step by step our programs, we should be able to do the same with our proofs, and knowing that they are stable all the way. And this is, of course, not always possible, and we can see it directly with our example here. If I take the definition of the optimization function and put it in the theorem, I get this equality that it's almost always not provable, because it's, of course, interpretation of a whole equals interpretation of some term, and we cannot put it. And more generally, the issue is that equality is not incremental. So the syntactic restriction of propositional equality is too strict, and it doesn't allow for incompleteness. And since equality appears everywhere, there's many properties that are not incremental. And there is an approach that addresses this issue, so it takes incompleteness in consideration. It's basically by reformulating the specification. And this is the approach that the Coq-R project took. It's a mechanism formalization of R. And so what they did, the approach is that they define a result monad, which represents the possible results of the interpreter. And in particular, they said, okay, this whole is going to be this case, this constructor. And then for the specifications, they defined this function result prop, which allowed them to specify what property each result should satisfy. And so in particular, they said, okay, the incomplete code is always true. No matter what the specification, it's just true. And so using this function, they can state any theorem, and they know that the incomplete part will be handled automatically, and they don't need to do any admits or anything. So this works, this is great. The only thing is that this is specific to this project and the monadic approach that they used, and that it's manually defined, so it's prone to human errors. And the last thing is that it's only on the conclusion. So the question is, what happens if you are assuming something of an incomplete program and so on. And so we wanted to take this approach and make it more systematic. So this brings us to our work right now, where we present a formal framework to support incremental certified programming by guaranteeing this incrementality of predicates, of properties, by using this reformulation approach. And so the first thing we introduce is a completion refinement relation to relate the different states of the program. We also introduce a notion of completeness to refer to the final state of development. And with this, then we define incrementality simply as monotonicity of reasoning over this refinement relation. And then for the reformulation part, we specify three properties that any reformulation should satisfy. The first one is, of course, incrementality, and which gives us the stability of proofs. The second one is recoverability, which says that once you finish your program and you proved your reformulated specification, then it should imply the original one. And this is important because it can happen that you do all the work, you finish, and only at the end you realize that your original specification was not true. So all of your work went to the trash. And in the very silly example, we could have the true predicate, which is incremental, that's great, but of course it doesn't say anything about our original specification. And finally, the third property is approximation, which says that the original predicate should imply the reformulated one. And in essence, what this is saying is that the reformulation process should not introduce any errors. And again, as a silly example, but we could have the false predicate, which allows us to recover the original one, but of course we cannot do anything with it. We cannot prove it. And so if a property satisfies these three other properties, then we call it an incremental reformulation. So then what we noticed is that there's a fragment of predicates that can be systematically derived. An incremental reformulation can be systematically derived. And I'm not going to show all of the examples, they are in the paper. But there's two things that I do want to emphasize, is that for the process of reformulation, the polarity of the predicate matters. So where you sit in an implication, whether it's on the goal or in the premises, it matters on how you reformulate. And that we add a reformulation for equality using this refinement relation. And so I have a specification here which makes no sense, I don't know what it is, but it's just to show that there's an equality on the premises and in the goal. And when we reformulate, what we do is replace equality with the refinement, but we switch the directions, and we also add some additional predicates. And there's more in the paper. There's also some simplifications that one can do on the reformulations and so on. And so once we had this, we implemented a ROC prototype with type classes, and we did 3 case studies, but I'm only going to show one, which is with ComCert. And what we did was we took the whole compilation pass, we took in specific the deadco elimination pass, and we made it incomplete. We basically took one branch of code and we removed it. And then we were able to still prove the correctness lemma of this pass. And the main takeaways that I want to show in these presentations were that, and that we learned from this case study, were how to reformulate complex inductive predicates, and on how to retrofit incompleteness into an existing project. And we tried, for instance, to follow an ammonetic approach, but we noticed that it was too costly because we had to change many signatures, and it was we thought it was too costly. And then what we ended up doing was that we added an extra constructor, but that also ended up being too. It wasn't a good solution because we duplicated a lot of code. And so what we took from this experience was that we needed some lightweight manner of introducing incompleteness into projects, and we think that probably exceptions is a good choice. So we are working towards an exceptional approach to working incrementally in certified programming. And that's it. Thank you very much.
Thank you. Yeah, questions?
Hi, Max New, University of Michigan. So in Agda, using holes, you can put holes in your programs and your proofs. You already get a lot of incrementality.
Yep.
So which of these one of these properties is not satisfied by it?
The thing with Agda is that the holes are basically axioms, and they don't have any computational content. So basically, if you try to prove something about them, and sometimes you get stuck terms.
Okay. Oh, so you want to have like canonicity type thing, even in the presence of the holes.
Yeah.
Okay.
And it's even worse. Oh, sorry, maybe I need to take this. It's worse if you have, for instance, recursion, because then you start getting some weird stuck terms, and then you cannot prove anything. You're back in the same spot as before.
Okay. Yeah. Thank you.
Welcome.
Well, thank you again.